Show that G equal to Z equal to cos theta plus I sin theta, where theta is real, is an abelian group under multiplication. Now we want to show that Z comma cross is an abelian group. For this, we want to show that 5 laws. First one is closure law, second one associative law, third one existence of identity element, fourth one existence of inverse element, finally commutative law. For this we are taking three elements Z1, Z2, Z3 belongs to G. Z1 is in the form cos theta plus cos theta 1 plus I theta 1. Z2 equal to cos theta 2 plus I sin theta 2. Z3 equal to cos theta 3 plus I sin theta 3. Closure law means consider any two elements of given set, do operation. If the resultant is also belongs to the set, then we can say that closure law is satisfied. So consider Z1 into Z2. Substitute Z1 value and Z2 value. We already know that cos theta 1 plus I sin theta 1 can be written as e power I theta 1. Similarly, cos theta 2 plus I sin theta 2 can be written as e power I theta 2. Bases equal, add powers. Here I is common, that's why we are going to get e power I into theta 1 plus theta 2. Again, change this e power I theta 1 plus theta 2 in terms of cos and sin. Then we get cos of theta 1 plus theta 2 plus I sin theta 1 plus theta 2. Observe this resultant is in the form of elements of Z. Therefore, Z1 into Z2 belongs to G. That means closure law is satisfied. Next, we want to show that associative law is satisfied or not. For this, we need three elements. Those are Z1, Z2 and Z3. Now, Z1 into Z2 into Z3 equal to, we have already Z1 into Z2. Substitute. We have Z3 also. Substitute. This one is equal to, this step can be written as e power I into theta 1 plus theta 2. This term can be written as e power I theta 3. Again bases equal. So I is common, theta 1 plus theta 2 plus theta 3. Bases equal, add powers. So expand this one, then we are going to get cos of theta 1 plus theta 2 plus theta 3 plus I sin theta 1 plus theta 2 plus theta 3. Next, we want to find out Z1 into Z2, Z3. Substitute Z1 and also the product of Z1, Z3. Now, Z1 can be written as, that means this term can be written as e power I theta 1. This term can be written as e power I theta 2 plus theta 3. Bases equal, add powers, observe I is common. So, we are getting e power I into theta 1 plus theta 2 plus theta 3. This is nothing but cos of theta 1 plus theta 2 plus theta 3 plus I sin theta 1 plus theta 2 plus theta 3. So, observe these two RHS, these two are equal. Therefore, we can say that Z1, Z2 into Z3 equal to Z1, Z2, Z3. So, associative law is satisfied. Next, we want to show that existence of identity element. Here the operation is multiplication. That's why identity element is 1. So, take theta equal to 0, then z equal to cos theta plus I sin theta. Substitute here cos theta. Theta is replaced with 0. I sin 0. We know that cos 0 is 1. Sin 0 is 0. So we are going to get 1. Therefore, z equal to cos 0 plus I sin 0 is the identity element. Now I need inverse. Consider z equal to cos theta. If you want, you can take z1. Cos theta 1, I sin theta 1. Multiplicative inverse of z1 is 1 by cos theta 1 plus I sin theta 1. But this element is not in the form of elements of z. That's why we want to change this element like the terms which appear in z. That's why multiply numerator and denominator with cos theta 1 minus I sin theta 1. One into anything is anything. Therefore, cos theta 1 minus I sin theta 1. Observe the denominators. Here we have one formula, that is a plus b into a minus b. The product of a plus b and a minus b is a square. That means cos square theta 1 minus I square sin square theta 1. We know the value of I square, that is minus 1. Minus into minus is plus. So, this term becomes cos theta 1 minus I sin theta 1 divided by cos square theta 1 plus sin square theta 1. We know the value of this denominator, that is 1. So, anything by 1 means anything. That means the inverse of cos theta 1 plus I sin theta 1 is cos theta 1 minus I sin theta 1. This is in the form of element of given set. Therefore, inverse exists in the given set. Therefore, we can say that G comma cross is a group. Next, we want to show that commutative law. For this commutative law, we need two elements. Z1 into Z2 equal to e power I theta 1 into e power I theta 2. Bases equal, add powers. E power I is common, theta 1 plus theta 2. So thetas are real numbers. That's why I can write theta 1 plus theta 2 as theta 2 plus theta 1. This is again e power I theta 1 into e power I theta 2 into e power I theta 1. E power I theta 2 is nothing but Z2. E power I theta 1 is nothing but Z1. Therefore, we get Z1 into Z2 equal to Z2 into Z1. Therefore, commutative law is satisfied. Hence, we can say that G comma cross is an abelian group. If capital M is the set of all 2 by 2 matrices whose elements are real numbers, prove that capital M is an abelian group under addition. So here also we want to prove an abelian group. So for this, closure law, associative law, existence of inverse, existence of identity, and finally commutative law. We want to prove these 5 laws. So for this, we need 3 matrices. The orders of these 3 matrices are 2 by 2 matrices. That's why I am considering A as ABCD, B as EFGH, C as IJKL. Here A, B, C are elements of capital M. Here the operation is addition. Closure law. A plus B. A plus B means substitute A and B values. How we do matrix addition? First one plus first one, that is A plus E. Second one plus second one, that is B plus F. Third one plus third one, that is C plus G. Fourth one plus fourth one, that is D plus H. Observe this resultant matrix. These are all again real numbers. Why? Why means these elements are real numbers. These are also real numbers. Addition of two real numbers is again a real number. That too, this matrix order is 2 by 2. Therefore, if A, B are two elements of M, A plus B is an element of M. Therefore, closure law with respect to addition is satisfied. Next, associative law. For this, A plus B plus C equal to, we already have A plus B. Now I am adding C. C is IJKL. Same procedure you can follow. That means first one plus first one, second one plus second one, third one plus third one, fourth one plus fourth one. Then you are going to get this matrix. Next, we want to find out A plus B plus C. B plus C, this is B plus C. A is this one. Again add. Then we are going to get this matrix. Observe these two matrices are equal. Whenever RHS are equal, LHS are equal. So we can write this statement. Therefore, we can say that addition is associative. Existence of identity element. Here the operation is addition. Additive identity element is 0. So, E equal to 0, 0, 0 is the identity element. Next, inverse element. Inverse element means A plus minus A equal to 0. If we take A as A, B, C, D, then minus A equal to minus A, minus B, minus C, minus D. Substitute here A as A, B, C, D, minus A as minus A, minus B, minus C, minus D. Add corresponding elements, then you are going to get 0. That's why minus A equal to minus A, minus B, minus C, minus D is the inverse of A. From these 4 laws, we can say that M comma plus is a group. Next, we want to show that commutative law is also true. For this, we know already A plus B Write down, find out B plus A and observe the RHS. If RHS are equal, then we can say that A plus B equal to B plus A. Therefore, addition is commutative. M comma plus is already group. In addition to this group properties, it is satisfying commutative law. Therefore, we can say that M comma plus is an abelian group. So, this problem proof is completed.